It's important when considering simulation and various risk analysis approaches to understand that this is a statistical approach to safety, but that life-critical safety requires exceedingly small failure rates. Those failure rates are beyond what is typically addressed with a statistical approach, and that stretch to get that low a residual failure rate can violate intuition that people have about statistics. For example, when doing simulations, it is common to see teams looking at key performance indicators, KPIs, to help with improving quality of the automation. KPIs can address issues such as, are all the functions working? Is the functionality actually improving when changes are made to the software? And is the fault rate decreasing? When you have a system that goes from doesn't really work very well to works pretty well, KPIs and statistical performance analysis are a great idea. Typically, if you look at statistics, 3 sigma is almost all the area under a Gaussian distribution. If you talk to manufacturing quality folks, they'll say 6 sigma is really where you want to be, that if all your parts are within 6 sigma, then you have a really high quality system. It's also known that 6 sigma requires extreme attention to quality and is a significant effort to achieve. Well, let's say you could get your KPIs to the holy grail of 6 sigma. Where does that get you? 6 sigma quality is 99.99966%. This is commonly referred to as 5 nines. That means there's 5 nines in the decimal expansion. That's certainly better than 3 sigma, and it's certainly better than doesn't really work. But it's not enough for life-critical functions. Here's an example calculation. Let's say you're building a function that is activated about every 5 feet when you drive. So this is maybe obstacle detection or lane keeping or steering or something that has to trigger many times per mile. It is almost always right, but there's some probability it'll make a mistake. In this example, let's say we have 1,000 opportunities to get something right or wrong per mile. And there's 250 million miles per fatal crash because we want to be a bit better than an unimpaired driver. And for the purposes of a 6 sigma analysis, we're going to use a 1.5 sigma shift, which is a typical number. If you put that into a sigma calculator, you get 8.34 sigma for this life-critical function. That's a lot bigger than 6 sigma and way bigger than 3 sigma. In fact, it's 11 nines. That's twice as many nines as 6 sigma quality. This means that if you thought 6 sigma was hard, you're just getting warmed up on your way to life-critical software. As a practical matter, this means that for safety, statistical approaches are often not really useful because there's so many nines there that even the slightest mistake will blow your entire failure budget. Therefore, it's common in highly critical life-critical systems to just say you have to mitigate everything you can think of because the things you did not think of are going to eat up the entirety and possibly more of all your failure budgets. It's also important to note that this entire model assumes a Gaussian distribution, which is probably the most benign distribution you can think of for this sort of thing. And unfortunately, the real world is probably even worse than this.